Hello everyone, thanks for coming. Today we are going to do a review of our last week's lectures. So in this week, we talk about the positive definite matrices and the SPD decomposition. So for symmetric matrices, we wish to characterize the matrices when the projective form x transpose AX is greater than 0 for non-zero vectors x. So there are 5 equivalent conditions. The first condition, which defines a positive definite matrix, is equivalent to the matrix having positive eigenvalues and also the same as all leading principal minors are positive. Principal minor denotes the determinant of the first k by k block of the submatrix in the whole matrix. If all pivots without rule exchanges are positive, then that's also equivalent to positive definiteness. Finally, a positive matrix, definite matrix, can be decomposed as R transpose R, with R having independent columns. So there are 3 structures. A equals to Q lambda Q transpose, where Q is an orthogonal matrix. A equals to LD L transpose, where L is a lower triangular matrix. A equals to R transpose R. So we can relax the positive definiteness to positive semi-definite matrices. So positive semi-definite matrices, it satisfies the condition such that x transpose AX is non-negative. So equivalently, the matrix has non-negative eigenvalues, and the principal minors should not be negative. The pivots should also not be negative. A can be decomposed as R transpose R, with R having positively dependent columns. So the spectral form for positive semi-definite matrices is A equals to Q lambda Q transpose, where lambda is a diagonal matrices with non-zero diagonal elements. In this way, the projective form x transpose AX could be written as a summation from 1 to R lambda I yi, where y equals to Q transpose X. So semi-definite matrices allow 0 eigenvalues, and the least square problems would naturally produce a positive semi-definite matrix. Then we talk about the singular value decomposition. A equals to U lambda V transpose, where A can be a rectangular matrix, U is n by m, V is n by n. The sigma is a diagonal matrix. It can be a rectangular matrix. The singular values satisfy lambda 1 greater than lambda 2 greater than lambda r greater than 0. So the columns of U are eigenvectors of A transpose, while the columns of V are eigenvectors of A transpose A. Sigma I squared are eigenvalues of both A transpose A and AA transpose. So the geometric meaning is that AVJ equals to sigma J Uj. So what are the applications of the singular value decomposition? Since orthogonal matrices would preserve length, then the instability would come only from the diagonal matrix sigma. So singular values separate large and small directions, and then we can define the condition number of a matrix, which is the largest singular value divided by the smallest singular value. So it measures sensitivity of linear systems and would also reveal numerical rank and conditioning for a matrix. So key applications include image compression to get a low-rank approximation of the image, effective rank detection for a matrix, and polar decomposition for a matrix. Thanks for listening.